Previously, we've talked about integrating functions over a region of the plane. In this video, we'll talk about integrating functions over a curve. The ds in this notation refers to arc length, and this integral is called a line integral with respect to arc length, even though we're integrating over a curve and not necessarily a line. In this section, we'll work with parametrized curves. That is, a curve C that's parametrized by some vector function r of t, which can be written as a function x of t, the x values, and y of t, the y values, where t ranges between two numbers a and b. We'll only consider curves that are smooth, which means that under some parameterization, r prime of t exists for the values of t that we're interested in, and r prime of t is never 0. Intuitively, a smooth curve doesn't have cusps or corners. Or we'll sometimes consider curves that are piecewise smooth. They may have cusps or corners, but they can be divided up into finitely many pieces, each of which is smooth. Now for a smooth curve in the plane, parameterized by some vector function, as follows. Let's suppose we have some function f defined on the plane. We want to find this line integral with respect to arc length. This picture is intended to give the intuition. Here's the curve down here lying in the plane, and we can think of f as giving the height of a curtain above that curve. We can think of this line integral with respect to arc length as representing the area of the curtain. Let's consider this special case first. If the function is always 1, so the curtain has constant height of 1, then this line integral, representing the area of the curtain, should be exactly equal to just the length of the curve times that constant height of 1. Since timesing by 1 unit doesn't affect the numerical value of the answer, just the dimensions, the units, then that means that this line integral should just be equal numerically to the arc length. In other words, this integral of 1 ds should just equal to the integral of dx dt squared plus dy dt squared dt, because that's how we compute arc length. Now, if instead our function always had a constant height of 3, then the area of our curtain should just be 3 times the arc length, and more generally, it seems plausible that the area of our curtain should be given by the function's value at each point on the curve times that arc length factor. And that is exactly the definition of a line integral with respect to arc length. We can think of this expression here as representing ds. If you're not familiar with this expression for computing arc length, I encourage you to go back and look at the video on arc length to see where it comes from. Let's do an example and integrate this function. So here f of xy is equal to xy over the curve given by this parameterization. First, we know that this integral is defined as the integral from a to b of our function times the arc length element. From above, we know that x of t is t squared and y of t is 2t, so x prime of t will be 2t and y prime of t will be 2. Plugging all that into this, we get the integral of t squared times 2t times the square root of 2t quantity squared plus 2 squared dt. Let me simplify this, and I'll factor out the 4 and pull it out of the square root sign. Now, I wish I could do a u substitution and just let u be the stuff inside the square root sign. The only tricky part is that the du, which is 2t dt, is not exactly appearing outside here. It's still going to have a t squared left over. But if I just plunge ahead and try it anyway, here I'll change my bounds of integration also. So when t is 0, u is going to be 1, and when t is 1, u is going to be 2. So if I just try it anyway, we're going to get the integral from 1 to 2. My 2t dt becomes my du, so I'm going to have still a 2t squared left over. So I have 2t squared, I have my du, and then my square root becomes a square root of u. Now I need to convert this t squared into u, but that's not hard at all, because I know that t squared is u minus 1. So I can rewrite this as the integral of 2 u minus 1. I'll write this as u to the 1/2 du, and then if I simplify, grab a little more space, so that becomes twice u to the 5/2 times 2/5 minus u to the 3/2 times 2/3, evaluated by 2 and 1. After a little arithmetic, that becomes 8/15 times the square root of 2 plus 1. Those of you who like Riemann sums will be happy to know that it's also possible to define this integral in terms of the limit of a Riemann sum. And if we do so, we get an equivalent definition. If you're interested in seeing the details, I'll put them in a separate video. I do want to draw your attention to the fact that in order to compute a line integral with respect to arc length over a curve C, you're first required to find a parameterization of the curve C. Now, there are many ways to parameterize a curve, and you might wonder, well, if you parameterize it in two different ways, do you actually get the same answer for your line integral? Well, fortunately, you do get the same answer. The line integral of f over c with respect to arc length does not depend on the parameterization of c, as long as the parameterization goes from t equals a to t equals b for some numbers a and b with a less than b. If your parameterization is going from a bigger value of t to a smaller value of t, then when you compute your line integral, you're actually going from a bigger to a smaller number. It's kind of like you're integrating backwards, and you end up getting the negative of the answer you would if your parameterization went from a smaller number to a bigger number. In this video, we defined the line integral of a function of two variables with respect to arc length as follows. Here, x of t and y of t are the components of the parameterization of the curve. So basically, all you have to do to compute one of these line integrals is to find a parameterization of the curve. And I stated, but didn't prove, that it doesn't matter which parameterization you use. Then you use that parameterization to write all your x's and y's in terms of t. Then you substitute in your arc length factor for your ds. Now that everything's just in terms of a regular integral in the variable t, you can integrate.